All right, let's just dive right into this explainer. We are going to unpack a genuinely urgent analysis coming from the GTI, looking at exactly how the global telecommunications industry is gearing up for a massive, impending threat to our entire digital infrastructure. Honestly, it sounds a bit like the plot of a Hollywood thriller, but the threat to our secure communications is very real, and the race to fix it, well, it's already underway. So here's the crucial point: the ticking clock. Research giant Gartner predicts that by the year 2030, large-scale quantum computers are officially going to emerge. And look, we're not just talking about faster computers here. These machines will have the specific mathematical muscle to completely shatter the traditional cryptography that currently protects literally everything, from your personal text messages to the global banking system. 2030, that is right around the corner.
Now, if you're thinking we have plenty of time to figure this out, that timeline is shifting way faster than expected. Recent breakthroughs, like Google's Willow chip achieving quantum error correction, show us this isn't just some theoretical sci-fi concept anymore. Quantum computing is rapidly moving into practical application. What does that mean for us? It means this ticking time bomb could detonate much sooner than we initially thought.
Okay, so let's look at how our current security holds up against quantum math, because there is a stark contrast here. On one side, we have symmetric cryptography going up against Grover's algorithm. For this, we essentially just need a bigger lock. Doubling the key length, that keeps it secure. But on the other side, asymmetric cryptography versus Shor's algorithm, totally different story. Shor's algorithm can solve the complex math behind these systems in polynomial time. That means they are completely broken and totally insecure. We can't just make the lock bigger, we literally need an entirely new door.
And that builds a pretty clear map of the danger zone, showing us exactly which everyday encryption standards are exposed. While AES and the SHA hash functions really just need their parameters double to be safe, the actual foundation of our secure web traffic is in deep trouble. I'm talking about RSA and ECC. These are the asymmetric algorithms protecting almost all of our modern digital signatures, and they are entirely vulnerable. Their status simply reads insecurity.
So how do we defuse this? Well, the global cryptography community is racing to standardize something called post-quantum cryptography, or PQC. It's actually an elegant solution. These are advanced cryptographic algorithms specifically designed to run on the classical computers in smartphones we already use today. But, and this is the key part, they are completely mathematically resistant to the attacks coming from tomorrow's quantum computers. Think of PQC as the foundational manual for securing our future networks.
And the good news is, our defense is finally taking shape. Just recently, in August 2024, NIST officially released 3 new standards. First up, we've got FIPS 203, based on Crystal's Kyber, for transport security, and it's incredibly fast, by the way. Then there's FIPS 204, based on Crystal's dilithium, designed for digital signatures, which totally excels in verification speed. And finally, FIPS 205, using Sphinx Plus, which is absolutely perfect for securing firmware updates. This right here, this is our new arsenal.
But as you know, having the tools is really only step one. To understand the true stakes of this migration, we have to map the blast radius of the quantum threat across the 5 critical layers of our global telecom infrastructure. It's a massive, highly interconnected puzzle, and spoiler alert, every single piece needs an upgrade.
Let's start right in the absolute center of this blast radius, Layer 1, the 5G core network, the brain of the telecom system.
Now, the 5G service-based architecture is incredibly complex. Just think about it. Every single one of those connections, from the user access authentication when your phone first connects, to the communication channels bouncing between all those virtualized network functions, relies on cryptographic mechanisms. If a quantum computer cracks the RSA algorithms holding these specific pathways together, the literal brain of the network is entirely compromised.
Moving outward, we hit Layer 2, the signaling network, the command and control channels.
This layer doesn't actually carry your voice data or your texts. Instead, it carries the vital control commands that set up, maintain, and tear down those connections. It's essentially the nervous system. And a quick audit here reveals a massive vulnerability. The remote operation channels that engineers use to manage these devices, specifically the element management systems and SSL VPNs, are deeply dependent on algorithms like RSA, Diffie-Hellman, and elliptic curve cryptography. A quantum attacker wouldn't even need to attack user data directly. Just taking over the signaling management gives them the keys to the entire kingdom.
Next up is Layer 3, the time synchronization network, the rhythmic heartbeat of the grid.
This is something fascinating that we rarely even think about, right? Modern telecom networks require absolute precision. They operate on the exact same microsecond rhythm all across the globe. But the GTI analysis points out a genuinely terrifying possibility here. The network time protocols, NTP, often still rely on aging hashes like MD5 or SHA-1 for security. If a quantum attacker compromises those, they could easily manipulate the time signals. Desynchronizing the telecom infrastructure even by fractions of a second would cause massive data collisions, dropped calls, and basically systemic failure.
From the heartbeat, we move to the physical highways. Layer 4, the optical transport network, the fiber optic data highways. These are the massive fiber pipes transmitting immense volumes of data globally across continents and oceans. And while the optical fibers themselves are just transmitting light, the highly configurable equipment managing these massive data pipes, it relies heavily on VPN gateways and SSL connections for remote access and configuration. This reliance on Diffie Helmet and RSA means these critical infrastructure management points are essentially sitting ducks for Shor's algorithm.
Finally, at the very edge of our blast radius, we reach Layer 5, the bearer network, carrying the world's data traffic.
This is the IP-based workhorse that actually carries all the user data and signaling from source to destination, optimizing the traffic over those physical fibers we just talked about. Because it handles highly dynamic, optimized traffic management, its equipment is constantly communicating. The fact that it relies so heavily on exposed SSH and SNMP protocols for this management, using algorithms like RSA and DSA, is incredibly alarming. An attack here could literally allow bad actors to reroute, intercept, or just flat-out drop massive swaths of the world's internet traffic.
So, seeing the absolute scale of this vulnerability across all 5 layers brings us to the next big question, the migration challenge ahead, diversifying our defense.
How on earth do we diffuse this threat across these deeply integrated systems without breaking the internet in the process? Well, it requires a highly diversified defense. NIST is already preparing for the next phase. While we have those initial 3 standards we discussed earlier, in October 2024, NIST announced a second round of candidate algorithms for quantum-resistant digital signatures. Look at the variety here. We've got code-based, isogeny, lattice-based, multivariate. The strategy here is absolutely crucial. By diversifying the underlying mathematical approaches, we ensure that if a future quantum breakthrough suddenly compromises one technical route, the other routes are going to stand strong and protect the grid.
And that brings us to the ultimate question we all have to face. We have the blueprint for post-quantum cryptography. The brilliant minds in the cryptography community are delivering the tools. But when you look at the immense scale of our global telecom networks, the millions of connected devices, those deeply embedded vulnerable algorithms in our core, signaling, and transport layers, the challenge is staggering. The technology to save us exists, but the race to implement it is really just beginning. Quantum computers are coming, and that ticking clock is approaching zero. Will we migrate in time? Thanks for joining me on this explainer, and I'll catch you on the next one.